me if you see it. You see my presentation? So today we're gonna be a bit shorter. Like we're gonna do 30 minutes and 30 minutes of questions. Massimo is not here. I mean, he can come if I really need, but I think for this topic, we can handle it by ourselves. So this is our 7th class of Get Started in OpenSees with STKO. Today we talk about definitions and condition. We're still in our theory realm. I know everybody is very eager to start to do some real modeling and practicing what we're learning, but it's important that we understand all the steps before we dive into the models. Next week, on the 14th of July, we're gonna have an introduction on mesh analysis, and then the 2 weeks after, we're gonna have 2 double features on the analysis command. So all of the settings that you have to put in order to run your analysis in the analysis command, both static and dynamic. So today we talk about definitions and conditions. Definitions are not just time series, but today we talk about the time series because they're the one that 99% of the time we're gonna use. And conditions are constraint, loads, and masses. So both of the 2 words, definitions and conditions, are in blue because these are words that do not exist in OpenSees. These are words that we use in STKO as a container of all of other commands that are already in OpenSees to kind of put things together. But you will not find these words in OpenSees, not in OpenSees documentation. If you remember from our first class, this is the scheme of the abstraction of OpenSees. In the domain, we have the load pattern and the constraints, single point and multi-point constraints. Then in the load pattern, you can add different commands. It's like a bit of a container. The most common load pattern we use is the plain pattern. And in it, there are ElementalLoads, NodalLoads, and even single point constraints. We're gonna talk about what they are, but in this case, inside of the load pattern, they are prescribed displacements or rotation, prescribed nodal values. Instead, outside of the load pattern, there is some single point constraints commands, but not an SP command. So the SP command is inside the load pattern here, while single point constraints command, like it's fixed, are outside of it. Time series are used inside of the load pattern. This sounds very complicated, but it's gonna be quite clear as we go forward. But time series can also be used in other occasions, for example, referencing uniform excitations or ground motions. But today we talk mostly about load patterns. All of these abstractions are contained in STKO inside these 2 main, let's say, groups, definitions and conditions. There's something extra. In our condition, there are also masses, which in OpenSees are actually just applied at the nodes. So when you write your Tickle script in your program, you will just either use the command mass or apply the optional tag of mass inside of the optional parameter mass inside of the node command. Instead, in STKO, you have to add a condition called mass. And there's also other things in definition, not just time series, but also friction models, random variables, very complicated stuff. As I said, we will not use so much of this. So let's just start with the practicalities. How do you create and assign definitions and conditions? So I switched just because there were more stuff to say about conditions. But if we start with definitions, definitions are created with the commands available in STKO. They are light gray when not used, and they're blue when they're referenced, but they will not be used ever. This is because they're just something that you kind of add to your model, but you don't have to apply to any geometry. It's something that you just reference instead of the analysis steps when you create a load pattern. So definitions are not assigned, just reference in the load pattern when you are at the analysis step stage. Instead, condition can also be created, deleted, cloned, and edited, but there's an additional color coding which is used. So whenever you create a condition that is not used, you will see that it's like blue, it's like gray. So you will not see it highlighted in the work tree. This means that you did not apply to any geometry or interaction. How do you assign a condition? This is really important because it's different from physical properties and element properties. You do not drag and drop from the work tree, but you select your target before clicking OK in the editor. Some conditions, as you may have noticed, have restricted selection. So when you are inside of the editor, you will be able to select only a few things. So for example, only edges or only faces. This we will talk about later later on in the presentation. So conditions has definitions. They are referenced inside of analysis step, but not really referenced, but actually added. So in load patterns and constraint patterns, the conditions are added to be able to use them in the analysis. If you do not put them in your analysis, they will not be considered. So maybe you define them all well in OpenSees, but you did not add it in load pattern, sorry, in STKO. So they will not be written in your TICO script. Why constraint pattern is like blue? Again, this is something that, this is a word that does not exist in OpenSees. So if you go on the OpenSees documentation and write constraint pattern, it does not exist. They just created the load pattern as a container for multiple loads because it was useful. But for constraints, there's not really the possibility to create multiple constraints. So you kind of have to create line by line everything that you add to your, in terms of single point and multiple constraints. This is something that we, for consistency, decided to name so that we can have like a structure to refer to. So starting with definitions. Let's say, what is a time series? Because this is the most used definitions that we said we're gonna use in our models. Generally, a time series, this is a very general description and does not apply to all the cases, is the relationship between the time in the domain and the load factor applied to the loads that you are assigning to your structure. So each time series object is associated to a load pattern object. We can see this here, like a time series object is associated to a load pattern object. Which contains the load to which you want to apply the load factor. So for example, if you have different loads that you want to apply with different time series, for example, keep some load constant and make some other loads increase linearly, you can create different time series and different load patterns and apply, let's say, different behaviors of the load factor application in the same analysis. So this is something that can be useful. Of course, time series are not just this. They act differently depending on what type of object they are referenced to. Actually, this one is wrong. Reference to? Yes. If associated, for example, with the uniform excitation object, which is not a load pattern object, it's something different. It is the acceleration, it's not the time. It is the acceleration or velocity applied to the constraint DOF of the structure. For example, when you apply a uniform excitation with a path time series, so something that's moving on up and down, for example, like a seismic input, you're gonna apply that acceleration to the DOF of the structure. So this can be quite confusing because these are the same concept in OpenSees. In other softwares, these concepts are separated. There are different commands to apply accelerations and other commands to apply load factors. Instead here, the command is the same one, to define what is it the behavior that you want your analysis to have. The same time series in OpenSees can be reused for multiple analyses. So when you are at the end of your analysis command, there is this crucial point where you can decide if you want to keep the load constant in the next stage of your analysis. And if you want to reset the pseudo time of OpenSees to 0 or to another number. If this number is editable, you can decide. So this is particularly important to reset the pseudo time in analysis with displacement control, for example, because the second stage will be using the pseudo time has a load multiplier. So if you don't reset it, it will be like getting already at 100% and applying 100% of your displacement as the first step. So this is a bit confusing, I think, because we talked about pseudo time. Let's kind of go back a little. So time in OpenSees is called pseudo time. This is because it's not really time all the time. Any analysis has to grow monotonically, but if the analysis is dynamic, the pseudo time is the actual time, it's real time. But if the analysis is static, that's a fictitious example. It just means that the analysis is proceeding forward. So if in static analysis, for example, this thing that I was talking about before here, the important part, if we are in load control with a linear time series, the time step of our time series would be considered as a load multiplier. But this is not always because, for example, if the time series is not linear, it will not be the load multiplier. But if we are in displacement control, the time step is exactly the load multiplier of your analysis. So it's really important to reset if your pushover is the second stage of your analysis. For example, because pushover is one of the most common displacement control analysis in static that we do in OpenSees and STKO. So just remember this, it's important even if you're writing your own Pickle scripts. So there's numerous time series you can use. Just an example, you can have a constant one, a linear one, a path as a cycle that you define, or a seismic excitation. Just remember that when you create one, you are in control of the units that you're creating. So for example, if I'm going here and creating a path time series, I can apply an interval that are between my steps, but also a factor. So this can be useful if my seismic input is in G, and maybe G is meters on second square, but I want millimeters. So I want to actually multiply my time series for a factor. Just remember, you can use these before, instead of like pre-processing your data. You can just do it directly in STKO. So going back to our presentation, this is all about definitions. Like there's not much more to know. So it's really easy to define them. You can do it at any time just before the analysis steps. So I mean, they are in the work tree at the top, but you can actually do it after. It does not matter in your modeling workflow. But you really need them if you need that. Even the constant one has to be defined all the time. You cannot run an analysis without a time series. Then we go to conditions. So as I said before, all of this that it's like inside of this blue square are conditions in STKO. The only thing that it's a bit different from the command that you actually find in the OpenSees documentation. So we have the fix command, the equalDOF, all of these ones, and the SP command, etc. But for NodalLoads, we don't have actually the load command, because it would be kind of tedious to select each node and define each load that you want to apply to it. This is because, taking a step back, we're doing a finite element modeling. Our loads are assigned to the nodes. This we all know. And there's just a special case in which loads are integrated on the beam length. And this is because we know that the element we're applying it to is a beam. So in OpenSees, they created this command that we can use to just define a linear load instead of a nodal one. But what instead all of these commands do, even if you can apply them on different kind of geometries, is just anyway using the load command to transform the load that you are applying into a nodal one. So just so you know, every load that you apply in STKO and OpenSees, except ElementalLoad, LLoad, all of them are nodal loads, okay? And then of course, there are some automations that we added. The surface load, for example, that we talked about in our 4th class, that was actually kind of useful. I mean, you saw that you can apply the load of a slab without needing to calculate your edge load and even your nodal loads. So that's quite easy. And more, of course, in condition, there are the masses. As we said in OpenSees, masses are added when we create the nodes or with the mass command. Instead, in STKO, we go in conditions and we add the mass as we add any kind of load, okay? So, as I said at the beginning, there are 3 types of conditions: constraint, loads, and masses. Constraint prescribes the value of degrees of freedom, as imposing a condition to it, for example, support, or prescribed displacement, or it prescribes a relationship among different degrees of freedom. So there are 2 types of constraints: single point constraints or multi-point constraints. Single point constraints are applied to a geometry. So you can apply a fixed condition of, for example, a hinge to an edge, to a face, or to a node. But if you want a multi-point constraints, you need to apply it to an interaction, not to a geometry. A multi-point constraints is a relationship between the degrees of freedom of 2 or more nodes of different geometries. So for example, in this case, for the rigidDiaphragm we modeled in class 5, we have the master node of our structure and the slab nodes. So, okay, here there's no slab, but let's say the nodes of the beam elements of the diaphragm. So here we have constrained nodes, and then we have retained node we have the retain node, so the master node, and then we have constraint node to this retain node in the center. Single point, the most easy, there's just one command to create a single point constraint, which is the fix command. If you are in 3D and you're actually applying it to displacement and rotation, you have all of the 60 degrees of freedom available, and you can define which one you're fixing and which one you're not. This is all in the global coordinates. So just remember, it's not all conditions are in the global coordinates, apart from the one where it's specified. So for example, the surface load had a specific drop-down menu where you could define if the direction in which you were applying it was local or global, but normally it's all global. So here, I don't have my reference system, but X, Y, and Z are the conventional X, Y, and Z, and the same for the rotation. I added here these words because these names here, because sometimes, for example, in a zero length, degrees of freedom are called like this. They're not called like we call them in STKO. Sometimes instead, there is no actual tag or parameter name for the degree of freedom. For example, in the fix command, as you can see, there is no, like, it's just number of degrees of freedom. There is no tag for it. So when it's that, we kind of try to specify it to help the user understand what is it that they're using. But when this was the, let's say that the words chosen by the OpenSees creator, we kept those. But just you remember from 1 to 6, this is always the same order. So it's always like displacement in the X, Y, and Z, rotation in the X, Y, and Z. So this is all for single point constraints. Instead, if we move to multi-point constraints, we have 3 types of the ones that are most used. You can see up here there are others, but today we talk about just these 3. equalDOF, rigidDiaphragm, and rigidLink. So in an equalDOF, the displacement of the constraint nodes is set to be equal to the one of the retain node. That's it, nothing special, nothing fancy. This is quite useful if you have geometries that you want to separate because of visualization purposes, but you still want them to be attached to each other. So you can actually model them with this kind of multi-point constraints applied to an interaction. Then we have the rigidDiaphragm multi-point constraints. We talked about this before. What is happening here is that the DOFs of the list of the constraint nodes are moving as if they belong to a rigid plane with the retain nodes. So they have to be all on the same plane. You cannot create an interaction, for example, that creates a bilinear surface. This will not work. rigidDiaphragm has to be a rigid plane, a plane. So the displacement of the constraint nodes will be equal to the one of the retain plus the rotation of the retain for the distance between the constraint and the retain. So for example, this node will move exactly like this one moves, plus the rotation of this node, of this one compared to this one. Just for, just an additional thing, I wrote here that you can create more than one rigidDiaphragm at the same time, because what is happening in OpenSees, if you want to create this 3 rigidDiaphragm in a 3-story structure, you will have to write 3 lines, rigidDiaphragm, direction, not tag. And you cannot assign more than one slave to the same rigidDiaphragm because of course it needs just one master, not one slave. What is happening here is that in STKO, you can create an interaction with more than one constraint node and a lot of retained nodes. Sorry, we went over retained node and a lot of constraint nodes. But when you assign the rigidDiaphragm, they will all be computed as different. So when you write your TCO file, you will have 3 strings: rigidDiaphragm, master nodes, retain nodes, blah, 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 etc. So this is really easy to do in STKO rather than in OpenSees by writing it down. What is happening with the rigidDiaphragm that it's important to remember is that it imposes a condition of 0 axial strain on the element that connects the constraint nodes. So when you're using sectional, like elastic sections that in which the neutral axis does not shift as a consequence of bending because of the plane assumption, like a plane section assumption. So this constraint has no effect on what is happening in the beam in terms of axial load and axial strain. But when you're using, for example, a fiber section in which the neutral axis does shift as a consequence of bending, this will cause the beam to undergo axial deformation, assuming you are in a simple 3D frame structure that it's like loaded to gravity and has a bending in their beams. So to constrain this axial deformation, you need actual force on the beam. And the magnitude of this can be significant. So you will have results in your large 3D frame structure with axial forces on your beams, and maybe you will not figure out where they come from. So this is a really easy example I will attach to today's presentation in the support files, but I'm not going to explain this example because it actually tackles topics like distributed and concentrated plasticity that we still haven't talked about. But still, anyway, you see here, in this case, this is our little table with a rigid diaphragm. It has axial load, and the result, if we create an axial release, we can actually avoid this effect and see the results of a structure as we expect them to be. There's a webinar Massimo did on this, so just look at that and you will understand the topic for sure. And then last multi-point constraint we have is the rigid link. So this is the same as a rigid diaphragm, but for 2 nodes. So the listed constraint nodes move has a rigid body in reference to the retained node. Of course, equalDOF and rigidLink are the same exact constraint, multi-point constraint, if you have the 2 points that are collapsing in one location. So if you're just moving them back together, you can apply an equalDOF or rigidLink, it will be exactly the same. Because in this case, we're adding the rotation coupling, and instead in the equalDOF, there's no, like displacement and rotation are uncoupled. So just remember, if you use a rigidLink with one of the 2 types, they're bar or beam, so translational and rotational. The only difference is in the rotational degrees of freedom. So now we talk about loads. As I said, they're just nodal loads apart from the ElementalLoad that we discussed before. Loads that are applied with all of these commands that you find in the menu load when you create a condition are NodalLoad objects, add to a specific load pattern at the end. There's a restricted selection when you use these commands in STKO. So when you create an edge force, you can only select edges. This is not so like fantastic. I mean, it's basic. You're assigning something, you can just assign 2 edges. You can just select edges. But what's important to remember is that if you created a condition and then you want to change it, for example, you made a face force, but now you want to do an edge force, and you switch, you know that in the editor you can switch from one to the other, and the selection that you applied it to will remain the same. This is true for physical property, element property, etc. So I'm just going to show you. For example, here I have this column selected in this column property. If I go here and I edit this property and I don't know, I choose something different like this, and then press OK, you will see that the selection, well, let me go out. The selection is still the same, it didn't change. This is true for conditions too. But what is important to remember is that if you switch from restricted selection to another, you will lose your selection. So you will lose your target of the condition. Just be aware of that, because sometimes you just forget it, and you can maybe stay hours thinking about what's wrong with your model, but that's it. That's wrong. That's wrong. What happens when you use one of these loads? As I said, STKO inside just transforms your load into a nodal load. So if you're applying it on a face, for example, this is a 1 unit area face with a unit load, 25% of this load goes on each of the nodes. That's easy, like no sweat. So this is what happens whenever you apply the face, a solid, or an edge load. They just go to the nodes. It's just for you not to make the calculations, to be honest. Then we have the NodalLoads. So ElementalLoads are just for beams, as we said before. You cannot use them on shells. You cannot use them on solids. What's the important, what's the easy things is that they integrate on the length of the beam directly without having to transfer them just to the nodes. So they're like specific for beams and useful if you discretize them just to one element. If you are discretizing your beam in a lot of elements, of course, the nodal load, the edge load that we said before, will just give a result that is the same as this one, not much different, because there will be more nodes, and so you will have a larger discretization and a larger approximation to the NodalLoads distribution. Then, as we discussed in class 5, we have a surface load command that is something that's just in STKO. This will create a mixture of these two. So if you have beams on the sides of your, of course, you will have beams on the sides of your slab. Part of them would be transformed into loads, part of them in NodalLoads. Just go and look in your script and see what happens when you write a TICO file of this. It can be interesting for you to go and see what is actually happening. And then lastly, as a load, we have a prescribed displacement. This is called SP because it's actually a constraint in a single point. I'm constraining a node to move in a specific way. So I'm applying a displacement, but it's not a load, it's a constraining of a certain movement. And yeah, this is pretty straightforward. You can just apply this in this way. What is like maybe something that I didn't mention before can be useful. If you apply your force like this, you can change the mode of the way you apply, for example, an edge force to function. And here we'll be able to actually write some function of the coordinates of your structure. So if I say, I want the edge of this to be in function of X and to the, like divided by 2, the distribution will be based on the X of the structure in the local direction. So, or the global direction. Here you can choose, for example. So if you choose the local direction, and you have X going in different ways for all the beams, this can be useful, that you're saying your load has to grow, yeah, in this way. So this is something you can use not to make calculations. We use that in this model. You remember we divided Z for the value we wanted to apply so that it was an increasing value growing with the height of the building for the pushover. Of course, this was a very basic example. You can do it refinedly and just apply, I don't know, proportionally to the mass, if you know what's your mass distribution. Finally, we have masses. So masses, as I said, they do not need to be referenced in the analysis step. They will always be black in your work tree. You construct, this is wrong, forgot. Yeah, this is the command, but you're not writing the command here. You're just creating this condition in your model. There is a restricted selection. You need masses to make eigenvalue and dynamic analysis. So weight and mass, load and mass are different concepts in OpenSees and STKO. If you do not distinguish them and create them, they will not be computed. So remember that you need to create masses, otherwise there's not going to be any inertia in your model. And that's it for today. We were really good in 30 minutes. Thank you. Let's see if we have any questions from anyone.
Thank you, Francesca. May I ask one question?
Yeah. Yeah, please. The turn is ours.
Thank you very much for your very nice presentation. I'm wondering about I'm wondering about the time series you mentioned.
Yes.
And can we have, for example, if we have that the real earthquake ground motion, can we source in our program in STKO, or we have to define different parameters in STKO?
So you want to source your time series. So if you want, you can do this through like a custom command. You can write, I'm gonna show you my screen, otherwise you will not see anything. Yeah, so if you go here, before you're creating your load pattern, you can create a custom command and just write in TICO what is it that you want to source. And you'd have to define a tag for your time series. You have to create your time series, define a tag, and the tag has to be referenced here. Let me think about if it's really possible, because now I'm not so sure. No, it's not possible. So if you want to source your file, you will have to create your load pattern and your time series all in the custom commands. It's not possible to do a combination of both. Because when you go here, yeah, there's no like, let's say custom time series that you can create. I will ask Massimo if this is for real, but I'm quite sure it's like this. So what you have to do, you have to paste your values here. You can edit them, like define the start time, define a factor by which it has to be multiplied, all the values in your function. And I mean, it's a bit, there's a lot of options that you can use if you do this, but most, like, for example, when they do parametric analysis for creating multiple dynamic analysis with different seismic excitation, it's all done by TCO scripting. So it's not done through STKO XObject command. Does that answer to your question?
Yes, thank you very much. In short, can we source one single ground motion in STKO?
Yeah, you can do it through the custom command.
Or it's not possible?
In the analysis step, you can.
Yeah.
But you will need to define your load pattern also in the custom command. Is that clear?
Yes, thank you very much. Actually, today my internet connection is not
no problem.
So anyway, it's clear.
Okay, good. Jimmy asked a question about pendulum type isolation system. So we had a webinar on isolation systems. I can point you to it. I'm sure they talk about the pendulum type isolation system and the kind of interaction and conditions that you need to apply to create it. Let me share my screen. So here in our like training, e-learning courses, Massimo's courses, and then you go, yeah, number 19, seismic isolation using friction pendulum. And here is the full video you can watch. I'm sorry, there's no timestamps yet, but we will put them. Of course, it's a long video, I understand, but you will find the answers to your question there.
I have a question, if it's possible.
Yeah.
Just like, correct me if I'm wrong, because I didn't understand the part of the load constant in the analysis, because this, in the case, for example, of 2 stages where I apply the vertical load and then I do a pushover, in this case, even if I'm not doing a displacement control, I have to keep the load constant and reset the pseudo time?
I mean, yeah, even if you're not doing a displacement control, this is your question?
Yes, if I'm not doing a displacement control. I'm just doing a regular pushover, but not in displacement control.
I mean, this is what will happen is that your pushover will not start from 0 when it's drawn on the graph. Like when you're gonna plot your, the pushover, no, because the pushover is reaction forced against displacement. But if you're gonna plot, for example, a plot of your displacement against the time step will not start from 0. So you will have a graph that's floating in the space.
Okay. So every time if I have 2 stages, I have to put the load constant.
Well, I mean, it depends what you want to do. For example, in a pushover, it makes sense that the structure is still subject to the vertical load and then it moves horizontally.
Yes.
But I don't know, if you're doing 2 vertical analyses and you want to see the result of your structure to different vertical loads, you don't need to put the load constant.
We only leave this constant load check with the pseudo time reset if we are interested on having the last stage of the first stage constant for the second one.
Yeah, but do not like mix up. So because you can do this and do not reset the time step. So like, for example, I mean, I don't see when is it that you want to do this like this, but for example, if you don't, no, there's no way in my head that you will want to do this like this. But anyway, these are two different concepts. So load constant is keeping your loads constant, the one that were applied before, okay? Yes. So the loads are constant in the domain, okay?
Okay.
But then when you're actually resetting the time steps, what is happening is that, let's just run this so that we can, did I modify this? No. Oh, it's already here. So
we are seeing the presentation only.
Oh, sorry guys. Okay. Let me reload this. No, it's still working on. Let's wait a second. Anyway, what I was pointing at before is here. So you can click here and do not reset your time step, for example. Even if I don't see a condition in which you just want to keep your load constant and not reset your time step. But what's gonna change in a load control compared to the displacement control is that your results are not gonna be altered. It's just the time that it's altered. If I don't do this in the first analysis, and I don't click the pseudo time step, when I'm gonna look if instead of reaction force against displacement, I had plotted time ID against displacement, I would not have said, okay, my load constants reached 100%, so I know that I'm over the capacity of the structure already. So in displacement control, it's important because you will see a different result and you will not be able to interpret it. And also the load will be applied with the 100% load multiplier to your structure. With load control, it's not gonna alter the results. It's just going to, you will not have an analysis starting from this point, but it will start from a different point. If you, let's try this one. So I don't put this, and I have a displacement control analysis. And let's maybe put in my monitor, instead of displacement against reaction force, I want displacement against pseudo time. Let's see what happens in our monitor. Oh, yeah, this is the pusher from before, but it should be reset when it restarts. No, it did not do this. So we will see now on the x-axis the displacement, and on the y-axis the pseudo time. Yeah, so if you see here, we're now having the same result. We started applying a load factor that was already 100% of what we were applying before. So this is incorrect in terms of, I mean, this is a very easy model, so nothing is breaking now. But if you had a model with a lot of nonlinearity and you were just like pushing your structure 100% of the load factor at the first step of your pushover, it would not like converge at the beginning.
Okay, yeah, I understand. It's clear, yeah.
Okay. Anyway, if you're doing a load control and you do not reset the pseudo time, your results are fine.
Doesn't matter. But always, if I'm doing a displacement control, I have to remember to always reset
yes.
the time. Okay. And then I have another question regarding the conditions for the multiple points. You said that the equalDOF and the rigidLink were the same ones. In which condition?
If the point is, if the constraint node and the retained node are in the same location. So, for example, think about, I don't know if you've watched that that webinar on, how is it called? On rigid RC joints. Did you watch the webinar on RC joints?
Yes.
Yeah, so you remember that at the beginning, the procedure was to create a node in the joint and then distance it from the beam nodes and then move it far away, create some equalDOFs between the nodes and then put it back in.
Yes. Okay.
So when you move it back in, the interaction is actually collapsed in one point. We can do this, the example that I made with the face and the line on the side. So if I put myself here, I create a line. And then I create an interaction between this and this. If I have, for example, a pillar that is close to a wall, then if I move this line back in, the interaction is collapsed in one point. So I'm actually, the location of the constraint and the retained node are the same. In this case, the equalDOF and the rigidLink will give you the same thing because there's no actually, you see, there's no beam element. It's not actually a beam element, but there's no line in between the two nodes. So it means there will be no relative rotation. What is actually happening with the rigidLink is that you're not just saying that this node moves as this node, but for example, if this one moves and rotates, so moves and rotates a little bit, I cannot turn my, my cursor on the screen, but let's say this one does like this, but then also the beam connecting it with the other node is rotating. Actually, this is a bad example. So let's say these two nodes are connected by a beam. This is the I say first configuration, and then the beam is gonna be like this at the end. So then this interaction is gonna move like this. What is happening is that with the equalDOF, you're just gonna say that this point will move the same as this point. But you're not gonna say that on this node, the rotation that this distance actually gives will not be applied to this node. So they will just translate together. So translation and rotation are uncoupled in an equalDOF multi-point constraints. Instead, in a rigidLink, they are coupled. So you will be able to see both effects on the constraint nodes. It's quite, let's say, clear here. I said the constraint node will move exactly as the retained node. Instead, here I'm telling you that the constraint node will move as the retained node plus the rotation of the retained node for the distance in between the two.
Perfect. Great, thank you. I have another question, but I cannot remember, so I will read my notes again.
You have another question you cannot remember? Okay, just take some time to remember. We still have 10 minutes. We can take to remember more questions. Anybody else has something else you want to ask or actually add to this discussion? I don't know if you already used STKO and OpenSees, if you had already come across some things about conditions and definitions or anything else also.
Well, hello, do you hear me?
yeah, very like low, but I can hear you. Oh, sorry for the echo. Yeah, it's gone.
Now is it better?
Much better.
Yeah. So hello, I have a question. First, to clarify a concept for me. So besides adding self-weight in order to perform a gravity analysis, it is needed to add mass on each node to add the modal eigenvalue analysis, right?
Yes.
Yeah.
But
And second,
you can also apply face mass or edge mass or solid mass if you don't want to compute the nodal mass.
so in that part goes my second question, that is it an option to add masses with a certain shape, like a function? For instance, in my modeling, I have to add filling of bolts, so it has a certain distribution, so I wanted to know how to add, like, automatically.
You can, for example, if you know the mass, you can know the specific weight of your concrete in this case. So here it was a simplification to add the nodal mass, but in this model you could just add mass as an edge mass. So you know what's the distribution of the specific weight along the length of the elements, and it will be the same for everything. And then you can apply it like that, or you can add the mass, the mass of your slab as a face mass. What this will do, I don't know, was this slide there? Yes, I showed you. It's the same as for the load. It's exactly the same. So, I mean, this is a face load, but it might as well be a face mass. It will not write load, it will write mass command with the ID of the element and the mass in the direction in which you're putting. In the case of mass, the 6 DOFs are not X, Y, Z, not displacement, but mass in the X, Y, and Z, and rotational mass in the X, Y, Z. So you can use different shapes.
Yeah, thank you.
You're welcome. Just remember that units are important in this case, especially with mass. We see a lot of mistakes because you have the mass in kilograms, and so you divide to obtain the mass in newtons, but you are just using G in meter on second to the power 2 instead of millimeter on second to the power 2, because maybe your model is in Newton millimeters, so you cannot use G as it is, but you have to divide for 9,810 or instead of for 9.881. So just remember that everything is consistent, so also the mass needs to be consistent. And you can see this very clearly if you do any eigenvalue analysis. If the mass order of magnitude is wrong, you will see a period that is not in the order of magnitude you expect for a frame structure, for example. If it's not 0.1, 0.2, 0. Something, but it's 0, 0, 0.000 something, then something's wrong.
I remember the last question.
Go for your last question.
My last question, I promise. When we speak about rigid diaphragm, so we have a rigid plane. So we have all these hypotheses of like how it's going to behave. So everything is going to move in the same direction and with not any actual strain. But the thing is, if I want to make like this slab more flexible, like if it bends, can I do something?
Use a rigid diaphragm.
So there is no something similar that is like flexible diaphragm?
Well, I mean, there is in softwares that model masonry mostly, but in the rigid diaphragm condition, you cannot really assign a stiffness to your diaphragm. So it's just, you're saying, I'm behaving as a rigid body in which direction, that's it.
Okay.
So you cannot use this multi-point constraint to assign an elastic stiffness or softer stiffness to your plane. In that case, you need to use a shell and apply that stiffness to the shell. Using shell is not so bad. I mean, it's really easy. You just use, let me just show you. I actually
because in this case, I will have to like generate relationship between the shell and my beam element.
So what you mean is that you don't want to merge the shells with your beam elements?
I don't know if it's going to work.
Yeah, it is going to work. Like, are you talking about your equivalent frame model or?
For example, because now I'm doing it with the rigid diaphragm, but then I want to switch to a flexible one.
I don't know what Massimo told you, but did you start to model your, because I remember that you modeled your beam, you modeled your beam like this, your columns and your beam like this. So you had them at the corner. Do you still have them at the corner?
Yes, yes, I have it at the corner.
Okay, because I mean, this is something we discussed in theory in equivalent frame modeling. If you have, let's say, a facade, and you have an opening here. I mean, this is not gonna work like this by accident. I'm just going to, yeah, it doesn't work. What is happening? Let me snap to my grid. Okay, just let's scale this. Okay, so this is your wall, this is your door. So you will have your elements discretized by these lines. The beam element that it's actually, for example, representing the sphere should not be aligned here and then offsetted in this section to the right, but should be aligned at the center of it. And then what you have, it's actually a frame. Can I? Yeah, I can draw.
Yeah, because I have the columns, and with the section with fiber, I generate which is the section, and then with the offset, I put it where it should be.
So you will have your slab like this, and your column should be here. The next column should be here.
Yes.
Okay. So if you want to put a shell here, I don't see what is the problem. The important thing is that you create your face, you merge your face with the rest. You do not overlap the edges of the shell of the face that you're creating and the edges that you did before, because then you will have double edges. So just remember not to do this. And then you can just create an elastic isotropic plate fiber section, elastic membrane plate section. This one, you assign a stiffness, you assign a Poisson, and you assign an height. And then you create a shell element. Shell elements are the easiest elements of all because you don't have to do anything. Just define which kind of kinematics you want to apply, if it's a linear or a geometrical nonlinearity. And that's it. And then the important thing is that you mesh it with the mesh controls of the faces to be structured and quadrilateral, because if you use the shell Q4 is a quadrilateral element, so you need a quadrilateral mesh. You apply the mass to that face and the stiffness that you want to apply to your flexible diaphragm, and mesh everything, and the nodes that will end up in the middle, because of course, in this case, you're gonna have, I want to erase this. Yeah, you're gonna have, your mesh is gonna be divided like this, no? Because you will have to imprint these lines on your face before to be able to have a coherent mesh between the face and the rest of the structure. But then you will have all, like, you don't assign any property to the line, and you have a whole, like, just like this reticulated shell. You don't even need to define it more here.
So the thing is, I would have, so in this case, my slab will be a flexible shell. And in this case, these two red lines that are mimicking the columns should be center, but should be a force-based element.
Yes.
But and you think that they should be in the, like the axis should be in the position of the actual axis of my pier.
Yes, and then the beam that you define here, the one that it's like, it has your spandrel.
The spandrel, yes.
Yeah, I couldn't come up with the word in English. If you like, to me, the best way is to do it with an hinge beam, defining different length for the two hinged at each side, and then define the length of your spandrel where you want it. What is going to happen here is that it will, for example, in this case where that's not symmetrical, it will not be positioned in the center. Where is it that you have your actual opening? So it's actually a bit complicated because let's say maybe STKO, we still need to test very well how equivalent frame modeling works in STKO, but maybe the other things you can do is create 3 beam elements and this one assigned a rigid stiffness to these two, and then here your spandrel section.
So you said that it's better to generate three elements, and the two on the sides should be my rigid links, my elements with really high, my rigid joints, instead of adding the element of rigid joints that the Massimo explained to. Yeah,
I don't know. There's like, these are different options. Actually, we have some models made like this, but they're simplified. So the rigid joints are collapsed in the point. So the section of your pier just goes up and the mass of the pier is proportional to the real mass, but the section you visualize in STKO is as high as this beam. So it does not really account for the part that this part is a joint. It's just the joint is infinitely rigid and that's it. So maybe you can discuss a bit more this on the forum when we have time. You can just post some new questions.
I will do these two types and I will post it on the forum then.
Yeah.
One way and the other, and then to see which are the results and what Massimo has to say, or anyone else.
Yeah.
Thank you.
So we can also build up some more knowledge for our last webinars on this.
Great.
Anybody else has any more questions for today? This is, as you can see, this is really a class. I'm just thinking as I talk with you. So. Okay. So I think, dear 20 participants, today we're done. We meet each other next week. We're going to talk about all the analysis steps, commands that we have. So not just the analysis commands, but all the others too, the monitor, the load patterns, the constraint pattern, the region command. It's quite useful that you can use to add and take away parts of your structure if you don't want the results to be recorded on that part, on some parts of your structure. So just, yeah, I'll see you next week. Have a nice evening, day, night, whatever time.
Thank you very much.
Thank you.
Have a nice day, bye.
Bye, everybody. We have a chat.
Thank you.
Yeah, of course, the video will be available, so don't worry. It will be on YouTube by tomorrow evening, Italian time. Bye, everybody.